Hello, and welcome to Space for Sleep. I am glad you have found your way here tonight. Tonight, we are going to travel outward through the solar system, beyond Mars and beyond the asteroid belt, to the quiet, golden world that has probably made more people fall in love with astronomy than any other planet after Earth. We are going to visit Saturn. Saturn is not only a beautiful object, it is a scientific system, a gas giant made mostly of hydrogen and helium, a planet with powerful winds, a strange hexagonal storm at its north pole, a deep interior that we cannot see directly, a magnetic field that still puzzles physicists, hundreds of moons, and the most spectacular rings known anywhere in the solar system. Of all the worlds we can see through a small telescope, Saturn is the one that often feels least believable the first time you see it. There is a moment when the eye meets the eyepiece and the rings appear, not as a photograph, not as a textbook diagram, but as a real structure surrounding a real planet. And for a second the mind resists it. It looks too perfect, too balanced, too carefully arranged to be simply natural. It is natural. The rings are the result of gravity, collisions, tidal forces, ice, dust, and orbital mechanics. But understanding that does not make them less astonishing. It makes them more astonishing, because the more carefully we study Saturn, the more we discover that its beauty is not decoration. It is physics made visible. So tonight we will move through Saturn slowly and clearly. We will begin with the planet itself, its orbit, size, density, atmosphere, storms, magnetic field, and deep interior. Then we will turn to the rings, what they are made of, why they are so thin, why they have gaps, how shepherd moons shape them, and why they may be much younger and more temporary than they appear. After that, we will visit Saturn's major moons, especially Titan and Enceladus, two of the most scientifically important worlds in the outer solar system. And finally, we will follow the spacecraft that revealed Saturn to us, from Pioneer and Voyager to Cassini-Huygens, before ending with the questions that still remain open. This is not a lecture to memorize. It is a calm scientific journey built for a quiet night. You can follow every detail or let some of it pass by. Saturn will keep its own slow rhythm either way. Now, let's go to Saturn. Saturn is the sixth planet from the Sun, sitting at an average distance of roughly 1.4 billion kilometers, nearly 10 times farther from the Sun than Earth. At that distance, sunlight takes approximately 80 minutes to reach it, compared to the 8 minutes it takes to reach us. So the sunlight that warms Saturn's upper clouds left our star nearly an hour and 20 minutes earlier, slipping through all that distance in silence, to finally arrive at a world that rotates once every 10.5 hours and takes close to 29.5 Earth years to complete a single orbit around the Sun. That orbital period, almost 30 Earth years, gives Saturn a kind of deep, patient tempo that feels appropriate for the planet. By the time Saturn has traveled once around the Sun, a person born on the day of launch of the Cassini spacecraft would already be approaching 30 years old. Saturn's seasons unfold across decades. Its equinoxes and solstices are separated by 7 or 8 years each, meaning that from one Saturnian season to the next, entire generations of shorter-lived organisms here on Earth would live and die. This vast orbital timescale is part of why ancient cultures associated Saturn with time itself. Not because they understood the orbital mechanics, but because something in the slow, majestic movement of the planet across the background of stars communicated a sense of deep, unhurried duration that shorter period planets like Venus or Mars did not. Consider for a moment what 29.5 Earth years actually means against the scale of a human life. If you are 20 years old tonight, Saturn will complete its next full orbit around the Sun when you are approaching 50. The planet's pace is a reminder that the solar system operates on timescales that dwarf the individual human experience, that the orbits we observe in a single lifetime are themselves only brief snapshots of cycles that have been repeating, without interruption, for billions of years. Saturn is a gas giant, the second largest planet in the solar system after Jupiter. Its diameter is about 116,000 kilometers, making it roughly 9.5 times wider than Earth. If Earth were a marble, Saturn would be roughly the size of a basketball, perhaps a little larger. More than 760 Earths could fit inside Saturn's volume, which is a number large enough to be nearly meaningless until you try to imagine actually stacking that many Earths inside something, layer by layer, marble by marble. And yet, for all its size, Saturn is the least dense of all the planets. It is the only planet in our solar system less dense than water. If you could somehow find a bathtub large enough, a bathtub the size of a small ocean, and you filled it with water, Saturn would float. Not sink. Float. This is because Saturn, like Jupiter, is made primarily of hydrogen and helium, both among the lightest elements in the universe, and its enormous size means that even accounting for the compressed, dense material deep within its interior, the overall average density of the planet, all those hundreds of thousands of kilometers of gas, is just too low to beat liquid water. It is, in a sense, the closest thing to a soap bubble that a planet has ever managed to become. This low density has a practical implication that often surprises people. Despite Saturn's enormous size, its surface gravity, at the cloud tops, where atmospheric pressure matches Earth's sea level, is only about 1.1 times Earth's surface gravity. This is only slightly stronger than what we feel on Earth, a consequence of the planet's low density partly offsetting the effect of its great mass. You would weigh only about 10% more on Saturn's cloud tops than you do on Earth, even though you're standing on a planet hundreds of times more massive. The high surface gravity of a very dense planet and the modest surface gravity of a very large, very light one can end up remarkably close to each other. Saturn's rotation is fast, faster than most people would guess for such a large world. A single Saturnian day is only about 10 hours and 33 minutes, though determining this precisely took many years of careful measurement, because gas giants don't rotate like solid bodies. Different latitudes rotate at slightly different speeds, meaning there's no fixed surface point you can track the way you can track the rotation of a solid planet like Earth or Mars. Saturn's rotation rate had to be inferred through other means, through the behavior of its magnetic field, through the timing of radio emissions, through detailed modeling of its interior. And even now, the precise rotation rate of Saturn's deep interior is still, in some technical senses, a subject of ongoing scientific investigation. This fast rotation, combined with Saturn's relatively low density, gives the planet a noticeably flattened shape. Saturn is more oblate, more squashed at the poles and bulged at the equator, than any other planet in the solar system. The difference between Saturn's polar diameter and its equatorial diameter is about 10%, which is actually visible in high-quality photographs. If you look closely at a good image of Saturn, the planet doesn't look quite like a perfect sphere. It looks slightly compressed, slightly wider than it is tall, a subtle sign of how centrifugal force from all that fast spinning has been gently pushing its equatorial gas outward for billions of years. To understand Saturn's rings properly, it helps to first understand Saturn itself a little more deeply. So let's travel inward for a moment, through the layers of the planet, before we come back out to the extraordinary structures that surround it. One important difference between Saturn and Jupiter is that Saturn's lighter, lower density structure makes its atmosphere appear softer but does not make it simpler. In visible light, Saturn can look almost calm, as if the planet has been wrapped in a pale veil. But this is a visual illusion created by upper haze. Beneath that haze, the same broad physical forces that shape Jupiter are at work: rapid rotation, internal heat, convection, jet streams, condensation of cloud layers, and the constant rearrangement of gases under pressure. Because Saturn is so far from the Sun, sunlight is a weaker driver of its weather than it is on Earth. The planet receives less than 2% of the solar energy Earth receives at the top of its atmosphere. Yet Saturn is not meteorologically asleep. Like Jupiter, it still releases heat left over from formation and from processes inside the planet. That internal heat rises through the atmosphere, helping power winds and storms even in a place where the sun is faint and seasons last for years. That is one of the deeper lessons of the outer planets. Weather does not always require a warm surface and a nearby Sunday. On Earth, weather is tied to oceans, continents, evaporation, sunlight, and the turning of the planet. On Saturn, there is no solid surface, no continents, and no water ocean exposed to the sky. The weather is built from hydrogen, helium, trace compounds, internal heat, and rotation. It is a different kind of meteorology, but it is still meteorology. Saturn's outermost visible layer is a broad, relatively calm-looking atmosphere compared to Jupiter. Where Jupiter is dramatically banded with vivid contrasts between light zones and dark belts, Saturn's atmosphere appears more muted, more softly painted. Faint tans, creamy yellows, and pale oranges, without the sharp contrast that makes Jupiter's banding so immediately striking. This isn't because Saturn's atmosphere lacks the same kind of banded structure. The structure is there, driven by the same basic physics of rising and falling gas organized by rapid rotation. But Saturn's upper atmosphere contains a thick haze of ammonia crystals sitting above the main cloud layers, and this haze blurs and softens the contrast between bands, like looking at a detailed painting through a frosted window rather than a clear one. Beneath this haze, the atmosphere is more complex and more turbulent than it appears from a distance. Winds on Saturn are even faster than those on Jupiter, reaching speeds of up to 1,800 kilometers per hour near the equator, faster than any storm wind ever recorded on Earth, a speed that would, on our planet, be beyond catastrophic. And the winds on Saturn are not just fast. They are organized into broad equatorial jets that flow in alternating directions at different latitudes, similar to Jupiter, but extending much deeper into the planet's interior and reaching far higher average velocities. Occasionally, Saturn's apparently placid atmosphere is disrupted by a dramatic, planet-wide storm. These storms, sometimes called Great White Spots, occur roughly once every Saturnian year, about once every 30 Earth years, and represent one of the most dramatic atmospheric events in the solar system. When they occur, they can rapidly grow to encircle the entire planet within weeks, a vast ribbon of bright, turbulent clouds spreading all the way around Saturn's equatorial region, visible even through a small Earth-based telescope. Cassini observed one such storm developing in late 2010 and early 2011, watching it grow from a small bright spot into an enormous, planet-encircling band of turbulence that fundamentally disrupted the atmospheric patterns in Saturn's northern hemisphere for more than a year. The 2010 to 2011 storm was particularly remarkable for its scale and intensity. It began in the northern hemisphere in December 2010, appearing initially as a compact bright patch in Saturn's pale cloud bands. Within weeks, it had grown explosively, sending clouds and lightning spreading around the entire circumference of the planet. The storm produced lightning at a rate that dwarfed anything previously detected in the solar system. Cassini's radio and plasma wave instrument recorded thousands of lightning strikes per second, each one releasing far more energy than typical terrestrial lightning. By January 2011, the storm's head had traveled all the way around Saturn and caught up with its own tail, a closed ring of turbulence circling the entire planet. What made this storm structurally unusual was the way it eventually began to die. The turbulent head of the storm traveled around Saturn and collided with the stratospheric warm pocket its own early stages had created, and that collision essentially cut off the storm's energy supply, causing it to rapidly collapse. The aftermath left Saturn's northern hemisphere in a significantly altered state for months. The temperature of the upper atmosphere had risen dramatically in the affected region, and strange chemical patterns lingered in the cloud layers long after the visible storm had dissipated. Scientists studying the storm used it to probe Saturn's deep atmosphere in ways that would never be possible during quiet periods, learning about the circulation patterns and chemical mixing that operate far below the visible cloud tops, but are only revealed when something violent enough happens to bring deep material upward. Even on quieter days, Saturn's atmosphere is a place of constant, organized motion. The equatorial jet stream blows in a single broad band, moving in the direction of Saturn's rotation at speeds that would be unimaginable by any Earth standard. The mid-latitude regions host a series of alternating eastward and westward jets, each one separated from its neighbor by a sharp boundary, the kind of organized structure that arises naturally from the physics of a rapidly rotating atmosphere with no solid surface to disrupt the flow. These jets are stable over decades, possibly centuries, maintained by the same deep circulation that drives the planet's internal heat outward. Saturn radiates about 80% more energy than it receives from the Sun, slightly less than Jupiter's excess, but still significant, and this internal heat supply keeps the atmospheric circulation energized and active even in the absence of strong solar heating. The color palette of Saturn's atmosphere, muted as it appears from a distance, reveals more variety upon close inspection. The creamy yellow of the equatorial region gives way to slightly more orange and tan tones at higher latitudes. The polar regions, particularly the North Pole in its current season, take on a distinctly bluish tint in some wavelengths, an effect believed to result from the scattering of shorter wavelength light in regions where the thick ammonia haze is thinner or absent, allowing deeper, colder layers to be seen more clearly. Saturn's cloud colors, unlike Jupiter's dramatic palette, are muted by that high-altitude haze, but the underlying chemical diversity is there: sulfur compounds, phosphine, and other trace gases painting the cloud layers in pale but real distinctions that deepen with the scale of observation. Even more remarkable is a feature that sits at Saturn's North Pole: a persistent hexagonal cloud pattern, a six-sided structure that has been orbiting the planet since at least the Voyager flybys in the early 1980s, and likely much longer. Each side of the hexagon is roughly the length of Earth's diameter, about 12,700 kilometers, and the entire structure rotates with a period that matches the deep interior rotation of the planet, suggesting it's anchored to something fundamental in Saturn's dynamics rather than being a surface feature driven by conditions in the upper atmosphere. Inside the hexagon, a powerful polar vortex spins, essentially a permanent polar hurricane anchored at the exact geographic North Pole of the planet. The hexagonal shape itself is believed to result from a jet stream at that latitude interacting with the polar circulation in a specific way, a phenomenon that can actually be reproduced in laboratory experiments using rotating water tanks, which makes it both stranger and somehow more accessible at the same time. Deeper within Saturn, below the main cloud layers, the atmosphere thickens and warms. Hydrogen gas under increasing pressure eventually transitions toward a liquid state, then, at still greater depths and pressures, toward the exotic metallic hydrogen state we discussed in the context of Jupiter, where electrons flow freely through the compressed material, generating a magnetic field. Saturn's magnetic field is considerably weaker than Jupiter's, but still far stronger than Earth's. And it has one particularly unusual property. It is almost perfectly aligned with the planet's rotation axis, more so than the magnetic field of any other planet in our solar system. Earth's magnetic North Pole wanders and is noticeably offset from the geographic North Pole. Saturn's magnetic field is so nearly aligned with its spin axis that the offset is effectively undetectable with current instruments, a fact that actually creates serious problems for scientists trying to determine Saturn's precise interior rotation rate, since the usual method of tracking the wobble of a planet's magnetic field relative to its spin can't be used here. At the very center, Saturn likely possesses a dense core composed of heavier elements, rock, ice, and metal, with a mass somewhere between 10 and 25 times Earth's mass, compressed under pressures that would be impossible to replicate in any laboratory on Earth. Like Jupiter, recent models suggest this core may be more diffuse and extended than once thought, its edges blurring gradually into the surrounding layers rather than presenting a sharp, clean boundary. Saturn, in short, has no skin, no edge, no definitive surface anywhere. Just layer after layer of matter becoming progressively stranger, denser, and more extreme, from the outer haze of ammonia ice crystals all the way down to whatever sits at the very center, warm and compressed, and permanently hidden from every instrument we've ever built. Saturn's magnetic field deserves its own moment of attention because it is in many ways one of the most puzzling aspects of the planet. The field itself is substantial, stronger than Earth's, extending hundreds of thousands of kilometers into space, interacting with the solar wind and shaping a vast magnetosphere around the planet. But what makes it scientifically peculiar is its extraordinary alignment with Saturn's rotation axis. Most planetary magnetic fields are tilted relative to the planet's spin axis. Earth's magnetic axis is offset from its geographic axis by about 11 degrees, which is why compass needles don't point exactly toward the geographic North Pole. Jupiter's magnetic field is tilted about 10 degrees. Uranus and Neptune have magnetic fields dramatically tilted and offset from their rotation axis. Saturn, by contrast, has a magnetic field that appears aligned with its spin axis to within a fraction of a degree, the most precisely aligned planetary magnetic field known to science. This near-perfect alignment creates a genuine puzzle. Standard models of planetary magnetic field generation predict that some amount of tilt is nearly inevitable, arising from the turbulent, asymmetric motion of conducting fluid within the planet's interior. A perfectly symmetric fluid flow would produce a perfectly aligned field, but perfect symmetry is extremely rare in nature. Saturn's near-perfect alignment suggests that either there is some physical mechanism actively suppressing the tilt, or that our models of magnetic field generation are missing something important. One proposed explanation involves a layer of material within Saturn's interior that acts as an electrical filter, a region where the conducting properties of the material are such that it smooths out and symmetrizes the field before it reaches the outer layers of the planet. This hypothetical layer might lie between the outer hydrogen envelope and the deeper metallic hydrogen region, possibly associated with a transition zone where helium rains out of the hydrogen and settles deeper, creating a gradient in composition that affects the electrical conductivity of the surrounding material. The full resolution of this puzzle is still being worked on, and it represents one of the ways Saturn continues to challenge the models physicists build to describe planetary interiors. Saturn's magnetosphere, shaped by this peculiar axis-aligned field, creates its own complex environment of trapped radiation, plasma, and charged particles. Unlike Jupiter's radiation belts, which are among the most intense in the solar system, Saturn's radiation environment is somewhat milder, partly because Titan, orbiting within the outer magnetosphere, acts as a continuous absorber of energetic particles, sweeping its orbital region relatively clean compared to the inner magnetosphere. The moon Enceladus also plays a significant role, continuously injecting water molecules and ice particles into the magnetosphere through its geysers, which interact with the plasma environment and changed the local conditions in ways that are still being studied with data from the Cassini mission. Now let's go back, for a moment, to the long human history of watching Saturn, because that history is one of the quieter pleasures of thinking about this planet, and it stretches back further and with more careful attention than many people realize. Saturn has been observed since prehistoric times. It is one of the 5 planets visible to the naked eye, and ancient observers across many cultures tracked its slow, steady progression through the constellations. Babylonian astronomers, working thousands of years ago, compiled careful records of Saturn's position in the sky across decades, accurate enough that modern historians can reconstruct when and where Saturn appeared during specific years in the ancient world. The ancient Greeks associated Saturn with the god Cronus, god of time, a fitting association for a planet that takes nearly 30 years to complete a single orbit, moving through the zodiac constellations so slowly that a person might watch it for years without noticing its motion against the background of stars, only to realize, looking back across a decade, that it has traveled a great distance across the sky. In the 17th century, the invention of the telescope transformed Saturn from a wandering point of light into an actual object with discernible features, and initially created more confusion than clarity. Galileo, in 1610, was among the first to observe Saturn through a telescope, and he was immediately puzzled by what he saw. His instrument was not good enough to resolve the rings clearly, and so Saturn appeared to him as something strange, a triple object, as though the planet had a companion on each side, almost touching it. He described it in letters as appearing not alone, and puzzled over what he was seeing without arriving at an explanation. When he returned to look at Saturn 2 years later, the rings had shifted to a near edge-on position as viewed from Earth, and the companions seemed to have vanished, which perplexed him greatly. It was not until 1655 that Cassini-Huygens, working with a telescope of greater quality, correctly identified what Galileo had been seeing, a thin, flat ring surrounding the planet. Huygens published his explanation in 1659, initially encoding it as an anagram, a common practice at the time to establish priority for a discovery while leaving time to fully develop the idea, and later revealing the plain text. Saturn is surrounded by a thin flat ring, inclined to the ecliptic. It was the first time a ring system had been correctly identified anywhere in the solar system, and it represented a genuinely new category of astronomical object, something no previous model of planetary structure had included or predicted. Giovanni Cassini, working in the 1670s, extended this understanding by discovering the prominent gap in the rings that now bears his name, and by identifying 4 of Saturn's moons, Iapetus, Rhea, Tethys, and Dione, adding to the moon Titan that Huygens had discovered in 1655. Over the following 2 centuries, the story of Saturn's rings continued to develop through increasingly careful telescopic observations and increasingly sophisticated mathematical analysis. In the 1850s, the Scottish physicist James Clerk Maxwell, the same Maxwell who later formulated the equations of electromagnetism, mathematically demonstrated that Saturn's rings could not be solid or liquid, as some had proposed, but must be composed of independently orbiting particles. Any solid ring of the observed size, Maxwell showed, would be gravitationally unstable and would break apart. Only a swarm of separate, independently orbiting particles could remain stable over long timescales. This was confirmed observationally in the 1890s, when spectroscopic measurements showed that the inner parts of the rings orbit faster than the outer parts, exactly as independent particles following Kepler's laws would, rather than as a rigid disk rotating at the same rate everywhere. These theoretical breakthroughs, worked out at a desk and with a telescope rather than through a space mission, are a reminder that some of the most profound advances in our understanding of Saturn happened long before any spacecraft ever approached the planet. Through careful observation, clever mathematics, and the patient willingness to follow an idea wherever the evidence leads. The first spacecraft to reach Saturn were Pioneer 11, which flew past in 1979, and then Voyager 1 and Voyager 2, which made their historic flybys in 1980 and 1981 respectively. The Voyager encounters transformed Saturn from an object studied from a distance into a place, a system of real, complex, different worlds, revealed in detail for the first time by cameras that had crossed the outer solar system to get there. Pioneer 11 made the first close passage, providing initial data on Saturn's magnetic field, radiation environment, and the basic structure of the ring system, but its instruments were relatively limited compared to what followed. Its most lasting contribution was demonstrating that a spacecraft could safely navigate through the Saturn system without being destroyed by ring particles or other hazards, practical knowledge that made the subsequent Voyager missions possible. Voyager 1's flyby in November 1980 was a scientific revelation on almost every level. The spacecraft's cameras revealed the ring system in far greater detail than anyone had previously seen. Not just the broad bands visible from Earth, but hundreds of distinct ringlets, gaps, and structures within each ring, as though the broad bands had resolved into the individual threads of a densely woven fabric. Scientists had expected to see some fine structure within the rings, but not the extraordinary complexity that Voyager 1's images revealed. The rings appeared to contain thousands of individual ringlets, organized and structured on scales far below what any Earth-based telescope could resolve, suggesting that the physics governing the rings operated on multiple scales simultaneously. Voyager 1 also returned the first detailed images of Saturn's largest moons, including the first clear views of Titan, though Titan's thick orange haze meant that the camera saw only the smooth, featureless top of the atmosphere rather than any surface details. The images confirmed that Titan had a thick atmosphere and gave the first measurements of its composition and temperature profile, but the surface itself remained hidden. This limitation was frustrating and important in equal measure. Frustrating because Titan's surface was clearly fascinating, important because it directly motivated the later development of radar-equipped instruments aboard Cassini capable of penetrating the haze. Voyager 2's flyby in August 1981 complemented Voyager 1's findings and added its own discoveries, including the first close images of Enceladus, which showed a surface unlike any other moon seen at the time. Some regions heavily cratered and ancient, other regions completely smooth and fresh, suggesting geological resurfacing had occurred recently. At the time, scientists could identify the surface as unusual and young-looking, but the mechanism behind the smoothing was not clear. It took Cassini, arriving more than 20 years later, to reveal the geysers that were responsible, and to demonstrate that what Voyager 2 had glimpsed as a geological curiosity was actually one of the most significant astrobiology discoveries of the century. Both Voyager spacecraft also discovered Saturn's ring spokes for the first time, recorded the detailed structure of the F-rings braiding and kinking, identified several new moons that had not been detected from Earth, and measured winds in Saturn's atmosphere far stronger than scientists had anticipated. Voyager's data kept scientists busy for years after the flybys. The amount of new information returned by two spacecraft traveling at high speed through a complex planetary system, gathering data for a period of days at closest approach, was staggering. Much of what Voyager found about Saturn was only partially understood at the time and required later missions, additional observations, and more sophisticated theoretical frameworks to fully interpret. There's something worth appreciating about the Voyager encounters that goes beyond the scientific content of what they found. Both Voyager 1 and Voyager 2 were launched in 1977, before personal computers were widely available, before the internet existed, before most of the technology that defines contemporary life had been developed. They were designed, built, and launched by engineers using slide rules and early mainframe computers, and they traveled to Saturn, 1.5 billion kilometers from Earth, with navigation precision good enough to thread the gap between rings and moon systems within planned parameters. The images they returned of Saturn's rings were, by the standards of the era, extraordinary, and they came from a machine that had been traveling for 3 years through interplanetary space before arriving. Voyager 1, after its Saturn flyby, used Saturn's gravity to redirect its trajectory above the plane of the solar system, leaving the company of the planets entirely and heading outward into interstellar space. In 2012, Voyager 1 became the first human-made object to cross the heliopause, the boundary where the solar wind's influence ends and interstellar space begins, a milestone that was announced quietly and reverently by scientists who had spent careers following the spacecraft's long journey. It is still transmitting data today, its signal now taking more than 22 hours to reach Earth, growing fainter but still detectable by the Deep Space Network's largest antennas. Voyager 1 carries a golden record, a physical disk containing sounds and images of Earth, intended as a message to any intelligence that might someday find it. A gesture of reaching outward that is simultaneously scientific, philosophical, and deeply human. Let's also spend a moment on how Saturn formed, because its origin story shapes everything that followed. The rings, the moons, the composition, the position in the solar system. Saturn formed in the early solar system, approximately 4.5 billion years ago, from the same disk of gas and dust that gave rise to the Sun and all the planets. The process began with small particles of ice and rock colliding and sticking together, growing into larger objects called planetesimals, which themselves collided and merged into a solid core, a core that, once it reached a critical size of perhaps 10 to 20 Earth masses, became massive enough to begin gravitationally pulling in the surrounding hydrogen and helium gas from the disk at an accelerating rate. This process of gas accretion is believed to have been rapid once it began, possibly occurring over a period of only a few million years, which is very fast by planetary standards. Jupiter likely underwent the same process slightly earlier and more rapidly, which is part of why it ended up more massive than Saturn. Saturn, forming slightly farther from the Sun in a region where the density of available material may have been somewhat lower, or having started its gas accretion phase slightly later due to its more distant position, accumulated somewhat less material before the solar wind from the young Sun blew away the remaining gas of the protoplanetary disk, ending the period of gas accretion for all the outer planets. The distinction between the inner rocky planets and the outer gas giants is itself a consequence of where in the disk different materials could exist in solid form. Close to the young Sun, where temperatures were high, only rock and metal could condense into solid particles. The more volatile materials like water ice and ammonia ice couldn't exist in solid form close to the heat source. The rocky planets, Mercury, Venus, Earth, and Mars, formed in this inner, hot region, made primarily of what could condense close to the Sun farther out. Beyond what's called the frost line, temperatures were cold enough for water ice and other ices to remain solid, dramatically increasing the amount of solid material available for forming planetary cores. It was in this outer region that Jupiter, Saturn, Uranus, and Neptune formed, beginning with icy cores that grew large enough to capture enormous amounts of hydrogen and helium gas from the surrounding disk. Saturn's position, just outside the frost line but not as far out as Uranus and Neptune, gave it access to plenty of both solid material for core formation and gas for the envelope. making it the second most massive planet in the solar system. The exact timing and location of Saturn's formation continue to be studied through increasingly sophisticated computer simulations of the early solar system, each iteration revealing new details about how the planet's current positions and compositions can be traced back to conditions in the disk that existed billions of years ago. Conditions we can no longer observe directly, but can reconstruct through careful physical modeling and comparison with what we actually see in the solar system. Today, before we return fully to the rings, it is worth imagining what Saturn would look like from the surfaces of its own moons. From Titan's surface, were you to stand on it, protected from the cold and the methane atmosphere, you would look up and not see Saturn directly. Titan's thick, opaque orange haze would block the view completely. The sky would appear a perpetual orange-brown, dim and diffuse even at noon, with no clear distinction between the sun's direction and the rest of the sky. You would know Saturn was above you only because you had traveled there intentionally. The rings, the planet, all of it, invisible. Only sound instruments and instruments pointed upward in the right wavelengths would show you what you were orbiting. From Enceladus, the situation would be dramatically different. With virtually no atmosphere and a surface of nearly pure, fresh white ice, the sky above Enceladus would be black and filled with stars, sharp and unblinking. And above you, Saturn would dominate, an enormous sphere, its banded clouds visible in detail, its rings stretching in a vast, tilted arc across the sky. From Enceladus's surface, Saturn would appear roughly 10 times larger in angular diameter than our moon appears from Earth. Enormous, complex, impossible to ignore. The rings would cast shadows across the planet's cloud tops during equinox, or the planet's shadow would fall across the rings during certain orbital geometries, producing a deep, dark band cutting through the ring system that would be visible to a standing observer on the moon's surface. And below your feet, somewhere through all that ice, an ocean of liquid water would be quietly circulating, venting itself into the thin vacuum above you through the tiger-stripe cracks of the South Pole, sending plumes of water ice into space. The same plumes that feed the E-ring you could see glowing faintly around Saturn's outer system if you looked in the right direction with the right instrument. From Mimas, Saturn would be even larger in the sky, close enough that its full disk would subtend an enormous angle, so wide that you'd need to turn your head to take in the full sweep of it. The planet would fill a significant arc of sky, its storms and cloud bands visible with the naked eye, its shadow occasionally cutting across the rings during certain orbital phases, the ring system spreading outward from the planet's equatorial plane in both directions, narrowing to that impossible thinness when seen from certain angles and expanding to its full breadth when the geometry was right. None of these views have ever been seen by human eyes. All of them are reconstructions based on measurements, on photographs taken by spacecraft cameras, on mathematical models of what orbits and geometries imply about perspective. But the knowledge that these views exist, that they are real even if no human has ever experienced them, is itself a quiet and generous gift of science. The universe is full of views that no one has seen yet. Some of them we can now describe in detail because we understand the physics well enough, even though we haven't physically been there. The description is not the experience, but it is something, a kind of reaching across distance and time, toward a reality that remains just out of physical reach. And now, finally, the rings. Saturn's rings are the most extensive and most visually spectacular ring system in the solar system. They are not a single object, but a collection of billions of separate pieces, fragments of ice and rock ranging in size from tiny grains smaller than a grain of sand to chunks several meters across, all orbiting Saturn in a flat, broad disk that extends outward from the planet's upper cloud layers to a distance of hundreds of thousands of kilometers, and yet is And this is one of the most quietly astonishing facts about the rings. In most places less than about a kilometer thick. Some ring regions are thinner still, perhaps only tens of meters deep in the vertical direction. The rings are, relative to their width, thinner than a sheet of paper scaled up to the same proportions. An object that extends nearly 300,000 kilometers from edge to edge, and yet is thinner in most places than a 10-story building is tall. When you think about that ratio, hundreds of thousands of kilometers wide, tens to hundreds of meters thick, the rings stop feeling like a solid structure and start feeling more like a layer of frost on a vast, cold table. An almost impossibly thin sheet stretched across an enormous, flat disk around a planet. A geometry that feels improbable until you understand the physics behind it, at which point it starts to feel almost inevitable. The rings are made primarily of water ice, frozen water, in pieces ranging from tiny dust to boulder-sized chunks, mixed with smaller amounts of rock and dust. The ice content is what makes them so bright. Saturn's rings are among the most reflective structures in the solar system, catching sunlight and scattering it back in a way that makes them shine brilliantly, far brighter than the surface of Saturn itself. When Galileo first observed Saturn through his telescope in 1610, he couldn't quite make out what he was seeing. His instrument wasn't powerful enough to resolve the rings clearly, and he described the planet as appearing to have two companions, one on each side, as though Saturn were a triple world. Later, in 1659, the Dutch astronomer Cassini-Huygens, working with a better telescope, finally correctly identified the structure as a flat ring surrounding the planet, the first time a ring system had ever been identified anywhere in the solar system. One of the quieter pleasures of following Saturn over many years of amateur astronomy is watching the rings change their apparent angle. Because Saturn's axis is tilted about 27 degrees relative to the plane of its orbit, a tilt slightly larger than Earth's 23.5 degrees. And because Saturn takes nearly 30 years to complete one orbit, Earth-based observers see the rings at very different angles depending on where Saturn is in its orbit. Sometimes the rings are tilted toward Earth at their maximum angle of about 27 degrees, showing their full face and appearing at their most spectacular, wide and bright, and symmetrical on both sides of the planet. Then, over the following 7 or 8 years, the angle gradually diminishes as Saturn moves around its orbit, until Earth-based observers find themselves looking at the rings nearly edge-on, at which point the rings become nearly invisible, a thin, hair-like line crossing the disk of the planet, almost impossible to detect without careful observation. This ring plane crossing, when Earth passes through the plane of Saturn's rings as seen from the planet, is a rare and quietly remarkable event. For a brief period around that crossing, Saturn can appear through a telescope as a distinctly peculiar sight, a planet almost without rings, unadorned, as though the feature that defines it has temporarily vanished. The rings are not gone, of course. They are simply being viewed edge-on, and because they are so extraordinarily thin, their brightness collapses into a fine line. A ring plane crossing occurred in March 2025, though Saturn was too close to the Sun from Earth's point of view for a truly favorable observation. The next especially favorable edge-on views will come in the 2038 to 2039 period. These events are not only beautiful, they are useful. When the rings nearly disappear, faint moons and subtle structures become easier to detect, and the geometry of the system reveals itself in a way ordinary ring views cannot. The rings are traditionally divided and named using letters of the alphabet, roughly in the order they were discovered rather than in the order of their distance from the planet. Moving outward from Saturn, the main rings are the faint D ring, closest to the planet, then the C ring, sometimes called the crepe ring for its more transparent appearance, then the broad, bright B ring, the densest and most opaque of all, then a gap called the Cassini division, then the A ring, and beyond that, the fainter, narrower F, G, and E rings. The changing angle of the rings also changes the brightness of Saturn as seen from Earth. When the rings are opened wide toward us, they reflect a great deal of sunlight, and Saturn appears brighter. When they are edge-on, much of that reflective surface disappears from our line of sight, and the planet looks dimmer and more restrained. To an observer who follows Saturn year after year, the planet is not a fixed object with a single appearance. It is a slowly changing geometry problem, a world whose visible form depends on the positions of Earth, Sun, Saturn, and the thin disk of ring material in between. This slow change is one reason Saturn rewards patient observation. A single night can show you the planet and its rings, but a decade can show you the system breathing through geometry, the rings opening, narrowing, nearly vanishing, then opening again. Nothing about the rings themselves needs to change dramatically for the view to transform. The transformation comes from angle, light, shadow, and time. The B ring is the most visible from Earth and the most structurally complex. It is dense enough to be largely opaque to light passing through it, and contains a remarkable variety of internal structure, waves, spirals, alternating bright and dark bands, that are driven by the gravitational influence of Saturn's many moons orbiting both within and outside the ring system. The B ring is also home to some of the most dramatic phenomena in the entire ring system, including mysterious features called spokes, dark, radial markings that extend outward across the ring like the spokes of a wheel, lasting for hours before fading. First observed by Voyager and later studied in detail by Cassini. The spokes are still not fully understood, but they are believed to be associated with charged dust particles temporarily lifted above the ring plane by electrostatic forces linked to Saturn's magnetic field, creating transient shadow patterns visible as dark streaks across the otherwise smooth-looking ring. The Cassini division, the most prominent gap in the ring system, was first observed by Giovanni Cassini in 1675, the same astronomer whose name would later be given to the spacecraft, and appears to the naked eye through a telescope as a dark, empty space separating the B ring from the A ring. In reality, the Cassini division is not completely empty. It contains faint, sparse ring material, just far less than the dense rings on either side. The gap exists because of an orbital resonance with Saturn's moon Mimas. Any particle that tried to orbit within the Cassini division would complete exactly 2 orbits for every 1 orbit of Mimas, and this repeated gravitational nudge from Mimas over time has cleared out most of the material that once occupied that region, leaving the relative emptiness we observe today. The physics behind orbital resonances is one of the most elegant ideas in celestial mechanics, and Saturn's ring system is perhaps the best natural laboratory for studying it anywhere in the solar system. When 2 objects are in orbital resonance, their gravitational influence on one another is not random or averaged out. Instead, the repeated, periodic tugs occur at the same point in the orbit every time, building up constructively into a sustained force that can, over millions of years, push material out of a region entirely. It's the gravitational equivalent of pushing a child on a swing at exactly the right moment on every cycle. The effect accumulates, the amplitude grows, and eventually the swing goes far higher than any single push could have achieved. Mimas's gravity, acting on ring particles in the Cassini division through this resonance mechanism, has pushed them out of the gap as surely as a physical barrier would, though far more gradually and through pure mathematics. Other resonances with other moons create other, smaller gaps and structures throughout the ring system. The Yankee gap, maintained by Pan, and the Keeler gap, maintained by a tiny moon called Daphnis, are both the result of shepherd moons directly sweeping their orbital lanes clear. But the subtler structures, The waves and spirals that Cassini photographed in extraordinary detail throughout the A and B rings are driven by resonances with moons much farther away. Moons like Prometheus, Pandora, Janus, Epimetheus, and several others, each one tugging at the ring material from a distance, imprinting spiral density waves that propagate outward from the resonance point like ripples from a stone dropped in water, frozen in place by the steady ongoing resonance that created them. Some of these wave patterns are extraordinarily fine. Cassini's cameras, during their closest passes between the rings and Saturn's atmosphere in the grand finale phase, resolved structures in the rings at scales of a few hundred meters, revealing that the ring material is not smoothly distributed even within the main ring bands, but organized into a complex hierarchy of structure from the broad rings visible from Earth, down to the intermediate scale waves driven by resonances, down to fine-scale clumping and banding at the subkilometer level, potentially all the way down to individual particles and small aggregates at the meter scale. The rings, at every scale you care to look at them, reveal more organization and more structure than the scale below. The A ring, the outer of the two main bright rings, contains its own smaller gap called the Encke gap, maintained clear by a tiny moon called Pan that orbits within it. Pan, roughly 35 kilometers across and shaped a little like a walnut due to a ridge of ring material accumulated around its equator, sweeps its orbital lane clear as it circles Saturn, and its gravitational influence also creates wave patterns in the ring material on either side of the gap, like the wake of a boat moving through water. Beyond the main rings, the F ring is one of the strangest and most dynamic structures in the system. It is a narrow, braided ring that seems to twist and knot around itself in ways that appear almost deliberate, driven by two small shepherd moons, Prometheus and Pandora, that orbit just inside and just outside it. As Prometheus swings close on its slightly faster interior orbit, it periodically dips into the F ring's inner edge, pulling out strands of ring material in dramatic streamers that then drift and shear across the ring as time passes, creating the complex, kinked, braided appearance that has fascinated ring scientists since the Voyager era. Cassini watched Prometheus do this repeatedly over its 13 years of observation, and the patterns it creates are different each time, depending on exactly where Prometheus is in its orbit relative to the ring material it's disturbing. Inside the rings, collisions are frequent but usually gentle. Ring particles are not flying randomly through space like fragments in an explosion. They are all orbiting Saturn in nearly the same plane, in nearly the same direction, and neighboring particles follow very similar paths. When they collide, the relative speeds are often low, more like slow bumping and grinding than violent impacts. These countless small collisions help keep the rings flat. If a particle is nudged above or below the ring plane, interactions with other particles gradually damp that vertical motion, pressing the ring system back toward its extraordinarily thin disk. This is why the rings are both chaotic and orderly at the same time. At the level of individual particles, there is motion everywhere. Grains tumbling, chunks rotating, fragments colliding, little clumps forming and breaking apart. But at the larger scale, the system becomes calm and architectural. The randomness averages out. The repeated collisions and Saturn's gravity produce a disk so flat and structured that it looks, from a distance, almost manufactured. Ring particles also sort themselves by orbital speed. The inner particles orbit Saturn faster than the outer particles, following the same basic rule that governs planets around the Sun. Closer objects move faster. This means the rings do not rotate like a solid record. There is no single spin rate. Every distance from Saturn has its own orbital period. The rings are a disk of independent orbits, layered so finely that the eye reads them as one object, even though physically they are billions of separate journeys happening at once. The G ring and the E ring are both faint, diffuse, and extend to much greater distances from Saturn than the main ring system. The E ring, in particular, is exceptionally large and tenuous, extending from roughly the orbit of Mimas all the way out to the orbit of Titan and beyond, a vast, faint haze of microscopic ice particles spread across an enormous volume of space. And its source, discovered by Cassini in remarkable detail, is a moon called Enceladus, which we'll come to in a little while. There is also a ring not visible at all in ordinary light, the Phoebe ring, discovered by the Spitzer Space Telescope in 2009, an enormous, extremely faint ring that extends outward at enormous distances from Saturn, aligned with the orbit of the moon Phoebe, and believed to be composed of material knocked off Phoebe's surface by micrometeorite impacts. The Phoebe ring is so vast and so thin that it was missed entirely by all previous observations, noticed only when spacecraft sensitive to infrared light looked in the right direction and found the faint thermal signature of its dust spread across an incredible volume of space. Now, how did the rings form? This is one of the most actively studied questions in planetary science, and the honest answer is that we still don't know with certainty, though the evidence gathered by Cassini in its final years has reshaped what scientists think is most likely. For many years, there were two broad schools of thought. One held that Saturn's rings were ancient, that they formed at roughly the same time as Saturn itself, some 4.5 billion years ago, from material left over in the disk of gas and dust that gave rise to the planet and its moons. The other held that the rings were relatively young, geologically speaking, perhaps only tens or hundreds of millions of years old, formed from the breakup of a moon or a comet that ventured too close to Saturn and was torn apart by the planet's tidal forces. The evidence Cassini gathered in its final months of operation, deliberately plunging between the rings and the planet's cloud tops in a maneuver called the Grand Finale, strongly suggested the rings are younger than the solar system itself, perhaps no more than a few 100 million years old, and possibly between about 10 and 100 million years old. This conclusion came from careful measurements of how much mass is raining down out of the rings into Saturn's upper atmosphere, a process sometimes poetically called ring rain, and from the total mass of the rings, which is far smaller than would be expected if the rings had been in place for 4.5 billion years and been continuously eroded throughout that time. The brightness of the rings tells scientists something important about their age. Ice in space does not remain perfectly clean forever. Over time, micrometeorites and dark dust from the outer solar system should fall onto ring particles, staining them and reducing their reflectivity. If Saturn's rings had been present in their current bright form for the entire age of the solar system, many scientists would expect them to look darker and more polluted than they do. Their brightness is one of the clues suggesting that the main rings may be relatively young, at least compared with Saturn itself. But the interpretation is not simple. Ring particles collide, break, expose fresh surfaces, and redistribute material. Dark contaminating dust may not mix evenly. Some ring regions can appear younger or cleaner than others. So the age of the rings is not read from their brightness alone. It comes from combining brightness, mass, composition, pollution rates, ring rain, and dynamical modeling. Saturn's rings are not just beautiful, they are a forensic puzzle. They are evidence left behind after an event whose original object no longer exists. If the rings are truly only a few 100 million years old, then something destroyed a moon or possibly a comet. In that relatively recent geological past, recent on the scale of the solar system, though still extraordinarily long on any human timescale, and the debris spread into the flat disk we see today. The leading candidate for this destruction is a moon that wandered too close to Saturn, crossing what's called the Roche limit, the distance from a massive body within which tidal forces overcome the self-gravity of a smaller object and pull it apart. What that moon looked like, how large it was, what its history had been before its final approach to the planet. These are questions that may be permanently unanswerable. The records of its existence spread and scattered into billions of ice fragments, now endlessly orbiting in the rings. There's something quietly moving about this, if you sit with it long enough. The most beautiful structure in the solar system, the thing that most reliably takes people's breath away when they first see it through a telescope, is, in all probability, the wreckage of a world. A moon that no longer exists, torn apart by the gravity of the planet it orbited, its remains organized by the same physics that destroyed it into the most elegant, symmetrical disk you can imagine. Destruction and beauty, in this case, are simply the same story told from different directions. Saturn's rings exist because of a zone around the planet called the Roche limit, the distance within which the planet's tidal forces overwhelm the self-gravity of any object. Anything within the Roche limit that tries to clump together, that tries to accumulate into a larger body, will find that Saturn's gravity pulls its near side harder than its far side, and that differential pull is stronger than the mutual gravity that would otherwise hold it together. Within the Roche limit, matter cannot easily coalesce into moons. It remains fragmented, dispersed, organized by gravity into a flat disk rather than into discrete worlds. Outside the Roche limit, the situation reverses. There, gravity can do its constructive work, pulling small fragments together into larger bodies over time. This is why Saturn's moons orbit at distances beyond the main rings, and why the rings themselves occupy the inner zone where moons cannot easily form. The rings and the moons are, in a sense, on opposite sides of an invisible line, each existing in the region appropriate to the physics governing it. This also explains an observation that takes a moment to fully appreciate. Within the rings, there are no moons larger than a few kilometers, but there are thousands of what scientists call moonlets, tiny embedded bodies somewhat larger than the ring particles around them, which create small, local gravitational disturbances in the ring material and leave faint propeller-shaped wakes that Cassini imaged in remarkable detail. These moonlets represent, in effect, the largest structures that gravity can build inside the Roche limit. They grow until their own size starts to make them vulnerable to being torn apart themselves, and then they remain in an uneasy balance, neither growing into true moons nor being completely disrupted, sitting quietly within the rings, leaving their small propeller wakes like tiny, permanent ripples in an infinite, frozen pond. Saturn's system of moons is among the most diverse in the solar system. As of March 2026, Saturn has 285 confirmed moons, far more than any other planet currently known in our solar system. Many of these are small, irregular objects, likely captured or fragmented over time, and some are no larger than a city or even a stadium. But among the larger, more clearly formed moons, several stand out as worlds of genuine complexity and scientific importance. Two of them, Titan and Enceladus, are so important that either could justify an entire journey of its own. Let's begin with Titan. The small newly confirmed moons also matter scientifically, even if they are too tiny and faint to become familiar names. Their orbits tell a story about capture, collision, and fragmentation. Many of them travel on tilted or retrograde paths, moving around Saturn in directions and planes that do not match the orderly inner moons. This suggests they may be remnants of larger captured bodies that were broken apart by impacts, leaving families of fragments traveling together in related orbits. In that sense, Saturn's moon count is not just a number. It is a record of ancient accidents in the outer solar system. The contrast between the inner and outer moons is dramatic. Close to Saturn, The large regular moons orbit in the same general plane and direction, as if they formed from a disk around the young planet. Farther out, the irregular moons behave more like collected debris, captured objects, fragments, and survivors from the early solar system. Saturn's moon system is therefore not a simple family tree. It is a layered archive. Some members born with the planet, others captured later, others produced by collisions that shattered earlier worlds. Titan is Saturn's largest moon, and it is, in many ways, one of the most extraordinary objects in the entire solar system. It is the second largest moon in the solar system overall, after Jupiter's Ganymede, and it is the only moon anywhere that possesses a dense atmosphere. Not a thin wisp of gas, but a thick, substantial atmosphere with a surface pressure roughly 1.5 times that of Earth's. If you could stand on Titan's surface, you would need to breathe from an oxygen supply, because Titan's atmosphere is made primarily of nitrogen, the same gas that makes up most of Earth's air, but it contains no free oxygen, and the few percent of methane mixed in would not support human respiration. Still, in terms of atmospheric pressure, the experience would not be crushing. You'd simply need breathing equipment and warm clothing, since Titan's surface temperature averages around -179 degrees Celsius. Titan's atmosphere is so thick, and the gravity so relatively low. Titan is somewhat smaller and less massive than Earth, that if you could somehow strap large enough wings to your body, you could fly through it with less effort than a bird requires here on Earth. The air is thick enough to support flight with relatively modest wing areas. This remarkable fact inspired NASA's Dragonfly mission, a rotorcraft designed to fly from place to place through Titan's skies, land on different terrain, and study surface chemistry directly. Dragonfly is currently planned for launch no earlier than July 2028, with arrival at Titan in late 2034. It is not designed to detect life directly, but to study the prebiotic chemistry that may resemble some of the chemical conditions on the early Earth before life emerged. What makes Titan particularly extraordinary is its surface. Titan has lakes, rivers, and seas, not of liquid water, which would be frozen solid at Titan's temperatures, but of liquid methane and ethane. The same hydrocarbons we use as fuel here on Earth exist on Titan in a liquid state, filling depressions in the surface the way water fills lakes and seas here, evaporating into the atmosphere, forming clouds, raining back down, carving river channels, a complete hydrological cycle almost perfectly parallel to Earth's water cycle, but running on methane instead of water, at temperatures nearly 300 degrees colder. Titan's largest sea, Krakenmeer, is estimated to be roughly the size of the Caspian Sea, a vast body of liquid methane sitting in the northern polar region, its surface presumably still, since Cassini saw no evidence of waves significant enough to disturb the radar reflections from it, though some rippling may occur under the right wind conditions. There are also vast dune fields near Titan's equator, shaped by wind, made not of sand but of organic particles, dark and slightly tacky, drifting and accumulating into long, parallel ridges that stretch across huge distances of the moon's surface. At the molecular level, Titan's atmosphere is a chemical wonderland. Nitrogen and methane interact under ultraviolet light from the sun, even though that sunlight arrives much weakened at Saturn's distance, creating a cascade of complex organic chemistry, producing hundreds of different organic molecules that settle through the atmosphere and coat the surface in a reddish-orange haze. Some of these molecules are related to the same building blocks associated with the chemistry of early life. Scientists are careful to note that this does not mean life exists on Titan. The temperatures are too cold for the kind of biochemistry we associate with Earth life, and liquid methane has very different chemical properties than liquid water as a solvent for life's chemistry. But Titan represents a natural laboratory for the chemistry that might precede life, an enormous, slow, cold experiment in organic chemistry running on the largest scales imaginable, worth studying in detail, not because we expect to find living things there, but because of what it might tell us about chemistry in the universe more broadly. Cassini spent years observing Titan, passing by it more than 100 times during its 13-year mission, using radar to peer through the opaque orange haze and map the surface. In 2005, the European Space Agency's Huygens probe, which had traveled to Saturn as a passenger aboard Cassini, separated from the spacecraft and descended through Titan's atmosphere on a parachute, taking measurements and photographs during the descent and surviving for over an hour after landing on the surface. The images Huygens sent back during its descent showed a complex landscape of drainage channels carved into hills, flowing down to a flat, dark plain. The channels clearly carved by liquid flowing downhill, looking almost disturbingly familiar to anyone who's ever looked at an aerial photograph of a river delta on Earth, except that everything that should be blue is dark and hydrocarbon-drenched, and the sky above is a thick, impenetrable orange. The landing site turned out to be a flat, pebbly surface, pebbles of water ice, rounded by what appeared to be liquid erosion, sitting on a dark, slightly damp-looking surface of organic material. Huygens measured a temperature at the surface of -179 degrees Celsius and detected methane humidity in the atmosphere just above the ground, suggesting that the probe may have landed somewhere not far from where liquid methane periodically pools or flows. It was the most distant point on any solid solar system body that humanity had ever landed an instrument, a record that still stands today. Enceladus is Saturn's sixth largest moon, a small, bright world roughly 500 kilometers across that would, if not for what's happening beneath its surface, be a relatively unremarkable icy moon. But what's happening beneath its surface is anything but unremarkable. In 2005, Cassini flew close to Enceladus and made a discovery that fundamentally changed how scientists think about the possibility of life in the outer solar system. It detected active geysers erupting from the moon's south polar region, shooting jets of water vapor, ice particles, and complex organic molecules high above the surface and out into space. These geysers are not occasional or intermittent. They are ongoing, continuous, sustained eruptions from what appears to be a global subsurface ocean of liquid water sitting beneath Enceladus's icy crust, with the geysers venting through a system of long cracks in the ice near the South Pole that scientists nicknamed tiger stripes for their appearance in early images. What makes Enceladus so important is not simply that it has water. Water is common in the outer solar system, usually frozen hard into ice. What matters is that Enceladus appears to have liquid water in contact with rock, plus chemical energy and organic molecules. Those three ingredients, water, chemistry, and energy, are the reason astrobiologists pay such close attention to this small moon. A frozen world only 500 kilometers across has become one of the most compelling places to ask whether biology might emerge far from sunlight. On Earth, life does not require sunlight everywhere. Deep ocean ecosystems around hydrothermal vents survive on chemical energy released when water interacts with hot rock. That does not prove Enceladus has life, but it changes the question. The search is no longer limited to planets with warm surfaces and blue skies. It can include dark oceans hidden beneath ice, warmed by tides and chemistry instead of sunlight. Saturn, once seen mainly as the planet of rings, has become part of the larger search for habitable environments beyond Earth. This subsurface ocean is not merely hypothetical. Cassini's measurements provided very strong, essentially compelling evidence for its existence. The geysers themselves were sampling it and expelling its contents into space, where Cassini could fly through the plume and directly analyze the material being ejected. What Cassini found in those plumes included water vapor, ice particles, carbon dioxide, methane, molecular hydrogen, salts, phosphorus-bearing compounds, and a range of organic molecules, including complex carbon-rich chemistry that may help reveal how far Enceladus's ocean has traveled along the path toward prebiotic chemistry. The molecular hydrogen detected in the plumes is particularly significant. On Earth, molecular hydrogen is produced in abundance at hydrothermal vents on the ocean floor, where hot water interacts with rock in a chemical reaction called serpentinization. These hydrothermal vents are, on Earth, home to remarkable ecosystems of life that survive entirely without sunlight, drawing their energy from the chemical reactions at the vent itself. The presence of molecular hydrogen in Enceladus's plumes is consistent with the possibility that something similar, hot water interacting with rock on the seafloor of Enceladus's subsurface ocean, is occurring there right now. This would mean Enceladus might have, deep within its small interior, hydrothermal environments broadly similar to the environments where some scientists believe life on Earth first emerged. This does not mean life exists on Enceladus. The leap from the chemistry being present to the chemistry actually producing living systems is enormous, and there is no confirmed detection of life there or anywhere else beyond Earth. But Enceladus is now considered one of the most promising targets for the search for life in our solar system, because it meets, in one relatively small package, multiple criteria that scientists consider important: liquid water, a chemical energy source, organic molecules, and a long-term stable environment. And it has the remarkable additional quality of conveniently venting material from its subsurface ocean directly into space, where a spacecraft can sample it without having to land or drill. The ocean delivers itself, in small parcels, to whoever happens to be passing nearby. The material ejected by Enceladus's geysers that doesn't fall back to the Moon's surface escapes into Saturn's system, and much of it feeds directly into the E-ring, the broad, faint, diffuse ring extending across much of Saturn's outer system. The E-ring, in other words, is continuously replenished by the ongoing geological activity of Enceladus, a direct physical link between the ring system and the volcanic-like interior of one of Saturn's small moons. The ring is, quite literally, a product of that hidden ocean spread thin across space. Beyond Titan and Enceladus, Saturn's family of moons includes several more worlds worth pausing on, each different from the others in quiet but meaningful ways. Mimas is perhaps the most visually distinctive of Saturn's mid-sized moons, bearing an enormous impact crater called Herschel that covers nearly a third of its total diameter. The crater gives Mimas an unmistakable resemblance to the Death Star from science fiction, a comparison that is genuinely difficult to unsee once you've made it, though Mimas of course predates any such fiction by billions of years. The Herschel crater is so large relative to Mimas's size that the impact that created it must have come close to shattering the Moon entirely. Despite its dramatic appearance, Mimas is believed to be one of the more geologically quiet and featureless moons in Saturn's system. No active geology, no subsurface ocean confirmed, just an ancient, cratered surface preserving the record of billions of years of impacts. Iapetus is another moon with a striking and immediately recognizable visual feature. One hemisphere is extremely dark, nearly as dark as coal, while the other is extremely bright, one of the brightest surfaces in the solar system. This two-toned appearance puzzled astronomers for centuries after Cassini first noted, in the 17th century, that the moon was visible when at one point in its orbit and nearly invisible at another, as though it were only half-painted. We now believe the dark material on Iapetus' leading hemisphere is largely the result of the moon sweeping up dark dust raining inward from the outermost irregular moons, particularly material from the Phoebe ring, which coats the hemisphere that faces forward as Iapetus orbits. Once darkened, That surface absorbs more sunlight, heats slightly more than the bright hemisphere, and causes ice in the dark regions to sublimate and migrate toward the colder poles, where it refreezes, making the bright regions even brighter and the dark regions even darker in a slowly self-reinforcing cycle. The result is a moon that looks, from a distance, almost deliberately painted in contrasting hemispheres, a natural result of physics and orbital dynamics doing their quiet, patient work across billions of years. Rhea, Tethys, and Dione are three mid-sized icy moons, each with their own character. Rhea may have a very thin, temporary ring system of its own, the first ring system ever proposed for a moon, though this remains uncertain and debated. Tethys has a canyon system called Ithaca Chasma that stretches nearly 3/4 of the way around the moon, and Dione shows evidence of ancient tectonic activity in long cliffs and fracture systems across portions of its surface. None of these three moons have active geology comparable to Enceladus, but each carries in its surface the quiet record of a complicated, billions of years-long history of impacts, cooling, and subtle internal processes. Together, Saturn's moons represent one of the most diverse collections of worlds in the solar system. From the active volcanic-like plumes of Enceladus to the methane seas of Titan, from the coal and snow two-tone of Iapetus to the cratered silence of Callisto's Saturnian equivalent Mimas, from the enormous irregular bodies captured from the outer solar system in distant, tilted orbits to the shepherd moons nestled within the rings themselves, keeping their edges sharp. No two of Saturn's moons tell quite the same story, and the full story of Saturn's family of moons is still very much being written, mission by mission, flyby by flyby. Two more moons deserve mention before we move onward, each strange in its own way. Hyperion is a medium-sized moon unlike almost any other object in the solar system. Where most moons are roughly spherical, shaped by their own gravity into smooth, rounded forms, Hyperion is neither large enough nor massive enough for gravity to pull it into a sphere. Instead, it is an irregular, sponge-like mass of ice and rock, roughly 430 kilometers at its longest dimension, riddled with deep, sharp-edged craters that give it the appearance of something between a sponge and a porous rock floating in space. What makes Hyperion even more unusual is its rotation. Unlike most moons, which rotate in an orderly, predictable fashion, often tidally locked to their parent planet, always showing the same face, Hyperion tumbles chaotically in its orbit. Its rotation is genuinely chaotic in the mathematical sense, meaning it cannot be predicted far in advance. From one visit to the next, separated by even modest time intervals, Hyperion is likely to be oriented completely differently, with no repeating pattern, no predictable face, simply a tumbling lump of ancient ice following Saturn around its orbit in an endless, unpredictable roll. Phoebe is Saturn's outermost large moon and, unlike the inner moons, it orbits Saturn in the opposite direction to the planet's rotation, a retrograde orbit strongly suggesting that Phoebe was not born in Saturn's system but was captured from elsewhere, likely a Kuiper Belt object that wandered too close to Saturn billions of years ago and was caught by the planet's gravity. Phoebe's surface is dark and ancient, covered in craters, and its composition more closely resembles comets and Kuiper Belt objects than the ice-rich inner moons of Saturn. It is, in effect, a preserved relic from the outer solar system, spending its days in lonely orbit far from Saturn's rings and inner moons, following its backward, distant path, a captured visitor that has been circling its new home for billions of years. And it is Phoebe, its slow erosion by micrometeorite impacts over all that time, that feeds material into the enormous, faint Phoebe ring discovered in 2009, the widest ring in Saturn's system, invisible to ordinary light, but glowing faintly in infrared, a ghost ring surrounding the entire system at immense distances. No conversation about Saturn can be complete without giving proper attention to Cassini, the spacecraft that revealed more about Saturn than any instrument before or since, and whose final act of deliberate self-destruction stands as one of the most poignant events in the history of space exploration. The Cassini-Huygens mission was a collaboration between NASA, the European Space Agency, and the Italian Space Agency, launched in October 1997 and arriving at Saturn in July 2004 after a nearly 7-year journey through the inner solar system, including gravitational assist maneuvers at Venus, Earth, and Jupiter. The spacecraft entered Saturn's orbit on July 1, 2004, and what followed was 13 years of continuous, close-up observation. 13 years of orbits, flybys, measurements, and discoveries that fundamentally transformed our understanding of the Saturn system. During its mission, Cassini made nearly 300 orbits of Saturn, carried out repeated close flybys of Saturn's moons, flew through the geysers of Enceladus multiple times, conducted more than 100 close passes of Titan, discovered previously unknown moons, provided strong evidence for subsurface oceans, revealed the ring system in unprecedented detail, documented the development and progression of Saturn's massive 2010 to 2011 storm, imaged the North Polar hexagon and vortex in stunning resolution, measured the composition of the rings and atmosphere, and returned hundreds of thousands of images that shaped modern understanding of gas giants, ring systems, ocean worlds, and the diversity of environments possible in the outer solar system. By 2017, Cassini was running low on propellant. When a spacecraft exhausts its propellant, it loses the ability to maneuver, and an uncontrolled spacecraft in Saturn's system posed a risk. If it eventually drifted into Titan or Enceladus, it could contaminate those potentially life-bearing worlds with Earth microorganisms that might have survived the journey despite sterilization efforts. To prevent this, mission scientists planned a deliberate and extraordinary finale. Cassini's importance also lies in the length of its observation. A flyby can reveal a system in a moment, but an orbiter can watch change. Cassini saw seasons progress. It saw storms grow and fade. It watched the rings from different angles. It returned to Titan again and again, mapping what one pass could never map. It flew by Enceladus often enough to understand that the plumes were not a single event, but an ongoing process. The Saturn system became, through Cassini, not a frozen postcard, but a living planetary environment with weather, circulation, erupting moons, shifting shadows, and long-term rhythms. This long duration matters because outer solar system science often moves slowly. Saturn takes nearly 30 years to orbit the Sun, so Cassini's 13 years in orbit covered almost half a Saturnian season cycle. That allowed scientists to see how sunlight moved from southern summer toward northern summer, how the rings changed near equinox, how Titan's atmosphere responded to seasonal forcing, and how Saturn's own northern polar region emerged from winter darkness into sunlight. Cassini did not simply visit Saturn. It stayed long enough to watch time pass there. In the final months of its mission, Cassini was directed into a new series of orbits, diving repeatedly between Saturn's innermost ring and the top of the planet's atmosphere, a region of space no spacecraft had ever entered before, close enough to the planet that the rings loomed above and the atmosphere curved away below, threading the needle between the cloud tops and the ring particles with breathtaking precision. These 22 grand finale orbits gathered data that would have been impossible to collect from safer distances, directly sampling the composition of the ring material and the upper atmosphere, measuring the magnetic field more accurately than had ever been done, and returning images of the ring structure from angles and distances never previously achieved. On September 15, 2017, Cassini fired its thrusters to ensure it would hit Saturn's atmosphere rather than drifting away. It entered the upper atmosphere traveling at approximately 34 kilometers per second, oriented to keep its antenna pointed toward Earth so it could continue transmitting data for as long as possible. For about a minute, it sent back real-time measurements of the atmospheric composition at depths no previous instrument had reached. Then the aerodynamic forces overwhelmed it, and Cassini, the most sophisticated Saturn explorer ever built, the spacecraft that had spent 13 years circling a planet almost 1.5 billion kilometers from Earth, that had discovered ocean plumes and methane seas and hexagonal storms, that had carried the Huygens probe to Titan's surface and watched 693 sunrises over Saturn's rings, broke apart and was absorbed into the planet it had studied for so long. The final signal arrived at Earth at 11:55 a.m. Pacific Time on September 15, 2017. The mission control room at the Jet Propulsion Laboratory in Pasadena was filled with scientists, and when the signal ended, when the line on the monitor simply stopped, there were tears. Not because the mission had failed. It had succeeded beyond almost anyone's original expectations. But because something that had been present, that had been returning data and images and discoveries for 13 continuous years, was simply gone. There is a kind of grief specific to the ending of spacecraft missions that anyone who has followed one closely will recognize. A sense that something real and irreplaceable has been lost, even though it was always a machine, even though the data it gathered persists, even though the science it enabled will continue for decades. In Saturn's atmosphere, somewhere in the equatorial region, there are molecules that were once part of the Cassini spacecraft. Atoms of titanium, aluminum, and steel, originally processed from ore, shaped in factories, launched into space, carried across more than 3 billion kilometers, and ultimately dissolved into the atmosphere of the planet they spent 13 years studying. They are still there, slowly mixing into Saturn's hydrogen and helium, indistinguishable now from everything around them. There is something unexpectedly poetic about that ending. Looking ahead, the next chapter of Saturn exploration is already being written. NASA's Dragonfly rotorcraft mission to Titan, planned for launch no earlier than July 2028 and arrival in late 2034, represents the most ambitious direct exploration of a Saturn moon since the Huygens probe touched down in 2005. Unlike any previous mission to another world's surface, Dragonfly will not stay in one place. It will fly. It will lift off from one site, travel through Titan's thick orange atmosphere, and land at a new location to take measurements before lifting off again. Over the course of its planned mission, it aims to visit multiple sites, sampling the organic chemistry of different terrain types, investigating areas where liquid water and organic materials may once have existed together, and building a picture of Titan's surface chemistry detailed enough to tell us how far this cold world has traveled along the path of prebiotic complexity. The choice to send a rotorcraft rather than a rover was driven by Titan's unique properties. The atmosphere is thick enough and the gravity low enough that a multi-rotor vehicle can fly with relatively modest power requirements. Moving through the air allows Dragonfly to cover in minutes the distances that a rover might take months or years to traverse, and it allows the mission to sample environments far more diverse than any single landing site could provide. If all goes well, Dragonfly will transform our understanding of Titan from a fascinating but poorly sampled world to one of the most thoroughly investigated surfaces in the solar system beyond Earth and Mars. Parallel to Dragonfly's development, there has been growing scientific consensus around the need for a dedicated Enceladus life detection mission. Enceladus presents, uniquely in the solar system, an opportunity to sample the contents of a potentially life-bearing ocean without landing or drilling. The ocean delivers itself through its continuous geysers, directly into space where a spacecraft can fly through and collect samples. A future mission equipped with sufficiently advanced mass spectrometers and biosignature detectors, making repeated passes through the Enceladus plume, could potentially answer the question of whether biological chemistry is present in that hidden ocean with a directness and clarity unavailable anywhere else. The scientific community broadly regards such a mission as one of the highest priorities for solar system exploration in the coming decades. Saturn's broader role in the solar system is also worth appreciating on its own terms. Along with Jupiter, Saturn helps define the outer solar system's architecture. The gravitational relationship between the two giants, their near 5:2 orbital resonance, has shaped the history of the outer solar system in ways scientists are still working to fully understand. Some models of early solar system history suggest that Jupiter and Saturn together, during a period of orbital instability several 100 million years after the solar system formed, helped trigger a restructuring that scattered many smaller bodies inward, contributing to what's sometimes called the Late Heavy Bombardment, a period during which the Moon, Mercury, Mars, and Earth were struck by an elevated rate of large impactors, carving the great craters still visible on the Moon's surface. Today, if these models are correct, Saturn's gravity played a role in shaping the early bombardment history of Earth itself, a connection between a distant gas giant and the rocky planet where life eventually emerged that is humbling to consider. Saturn is also used regularly as a gravitational waypoint for spacecraft headed further into the outer solar system. Voyager 1 used Saturn's gravity in 1980 to redirect its trajectory out of the ecliptic plane and onto its path beyond the planets, still traveling through interstellar space. Cassini's initial arrival at Saturn involved careful gravitational maneuvering, and numerous proposed future missions to the ice giants Uranus and Neptune have included Saturn flybys in their planned trajectories. Saturn's mass and its position make it a reliable stepping stone, a gravitational assist point that has helped, and will continue to help, carry human instruments to the farthest reaches of the solar system. The question of how long Saturn's rings will survive is one that scientists have thought about carefully, and the answer depends significantly on their age and on how quickly material is being lost. If the rings are indeed only tens or hundreds of millions of years old, then they are in a relatively early and still bright phase of their existence. Over the next 100 million years or so, they will gradually erode away. Ring particles will slowly spiral inward under the influence of drag from Saturn's magnetic field and upper atmosphere, eventually raining down into the planet. NASA studies of ring rain suggest that Saturn may lose its main rings within roughly 100 to 300 million years, a long time by human standards, but a brief interval compared with the 4.5 billion year age of the solar system. This timeline means that if you could visit the solar system a billion years in the future, Saturn might still exist, still spinning on its flattened axis, still accompanied by its moons. But the rings might be a fraction of their current size, or perhaps reduced to the faintest of hazes, barely perceptible even to advanced instruments. Future civilizations, if any exist, looking at Saturn through their telescopes might see a gas giant that appears almost unadorned by comparison to what we see today, and they might have only the geological record preserved in Saturn's upper atmosphere, the mixed-in remnants of billions of years of ring rain, to tell them what the planet once wore around its equator. And it might also be the case that Saturn has worn rings before, that the rings we see today are not the first set of rings it has ever had, that other moons have been destroyed at earlier points in Saturn's history, creating earlier generations of rings that eroded away long before the current ones formed. Saturn may be a planet that occasionally destroys one of its own moons and wears the debris for a few 100 million years before the rings fade, only to repeat the cycle again when another moon's orbit eventually becomes unstable. If so, the rings are not a permanent feature of Saturn, but a periodic one, and we are simply fortunate enough to notice the fortune to be here during one of the ring-wearing phases. In some broader sense, what we see when we look at Saturn's rings is a process, not a structure. We see matter in transit, material that was once part of something larger, now dispersed into fragments, now slowly falling back into the planet that destroyed its source. The rings are, at every moment, both the remnant of something that used to exist and the beginning of something that will eventually return to Saturn itself. They occupy the middle of a long, slow story of creation and dissolution, beautiful precisely because they are temporary, because the state we're seeing is one that will not persist, because the universe doesn't hold the same configuration forever, but is always, slowly, moving towards something else. Let's pull back now and think about Saturn's rings not just as a scientific object, but as a philosophical one, as something that tells us something meaningful about the nature of beauty and impermanence in a universe governed entirely by physics. There is a question that sometimes arises in discussions of science and aesthetics. Does knowing how something works diminish its beauty? Does understanding that Saturn's rings are ice fragments drifting in orbits governed by gravity and resonance and tidal forces make them less beautiful than they seemed when they were simply mysterious? And the honest answer, for most people who have spent time with both the science and the direct observation of the rings, seems to be no. The scientific understanding adds to the experience rather than diminishing it. The fact that the rings are temporary, that they're the wreckage of a destroyed moon, that they're maintained in their sharp edges by small shepherd moons tugging at the boundaries, that they contain embedded moonlets leaving propeller-shaped wakes. None of this makes the first telescopic view less astonishing. If anything, knowing the story behind the image makes it richer, in the way that knowing a piece of music has a complex structure doesn't prevent you from feeling moved by it. Let's pause here and try to put the scale of what surrounds Saturn into some kind of human perspective, because the numbers alone don't quite convey it. The main ring system extends from about 66,000 kilometers above Saturn's center to about 140,000 kilometers above Saturn's center, a span of roughly 74,000 kilometers just for the main rings, meaning if you could lay the main ring system flat on the Earth's surface, it would extend from roughly London to just past Hawaii. The faint E-ring, fed by Enceladus's geysers, extends from around 180,000 kilometers above Saturn's center to nearly 500,000 kilometers, a diameter across the E-ring system of nearly 1,000,000 kilometers. If you placed Earth inside the E-ring and scaled things appropriately, the ring would be so vast that it would extend far beyond our moon's orbit. And yet, all of this spans a vertical thickness in most places of less than a kilometer, and in some dense regions perhaps only tens of meters. The ratio of width to thickness in Saturn's rings, at their densest, is comparable to a sheet of paper scaled up to the diameter of a medium-sized city. If you were to scale the rings up until the main ring system was as wide as a standard piece of printer paper, about 21 centimeters, the thickness would be far below what ordinary tools could easily show. Not visible, not easily measurable, almost absent for practical purposes. This geometry is not accidental. It is the inevitable result of orbital mechanics. Particles in orbit around a body that start with any slight vertical offset will, if they collide with other particles, gradually lose that vertical velocity through those collisions and settle into the flattest possible configuration, the orbital plane, because that's the lowest energy arrangement available to them. The rings are flat because flatness is what gravity and collisions naturally produce. Every ring system in the solar system, Saturn's, Jupiter's, Uranus's, Neptune's, shares this extreme flatness because the physics that produces them is the same everywhere. Consider, too, what it means that we can see the rings from Earth. The rings are more than 1 billion kilometers away. The light we see reflecting from them left the Sun about 80 minutes earlier, traveled all that distance to Saturn, bounced off ice fragments in the rings, and then traveled another billion-plus kilometers back toward us, arriving in our telescopes and in our eyes after another roughly hour-long journey through space. The light completing that full round trip, Sun to Saturn to Earth, takes about 2.5 hours total. The rings we see in the telescope are not the rings as they are right now. They are the rings as they were 2.5 hours ago, before we looked. This is a small delay by astronomical standards, nothing compared to the light years that separate us from the nearest stars, but it's a useful reminder that all astronomical observation is, in some sense, looking into the past. The further away something is, the older the image we see. Saturn's rings, at their distance, show us the rings from a couple of hours ago. The Andromeda Galaxy, visible to the naked eye on a clear night as a faint smudge in the direction of the constellation Andromeda, shows us light that left it 2.5 million years ago. The rings of Saturn and the smudge of Andromeda are both being seen in the same moment of earthly time, and yet one is showing us 2.5 hours into the past, and the other 2.5 million years. The universe, in this sense, is not a place but a layered collection of times, all arriving at our eyes simultaneously, each one telling us about a different moment in the past depending on how far away it originated. Before we drift toward the end of tonight's journey, it's worth spending a moment with what we still don't know, the questions that Saturn continues to hold unanswered, even after centuries of observation and decades of spacecraft visits. The precise age of Saturn's rings remains uncertain. Cassini's data strongly suggested the rings are far younger than Saturn itself, perhaps only tens or hundreds of millions of years old, but pinning down a more specific age has proven difficult. The measurement involves understanding how fast ring material is being lost and how much total mass the rings originally contained, both of which carry significant uncertainties. Different models, using slightly different assumptions about how ring particles interact and how the rain of ring material into the atmosphere proceeds, give somewhat different answers for the age. A future mission with instruments specifically designed to measure the ring mass and loss rate more precisely could resolve this. But for now, the age of the rings is known only within a range of a few 100 million years, a range that feels precise to a geologist but leaves a great deal of uncertainty about exactly when the moon that formed the rings met its end. The question of whether Enceladus's subsurface ocean actually harbors life remains entirely open. We know enough to say the conditions might be compatible with life as we understand it. Liquid water, a chemical energy source from hydrothermal activity, complex organic molecules. We don't know enough to say how closely those conditions resemble the conditions at Earth's deep-sea hydrothermal vents in the specific ways that matter for biology. A future dedicated Enceladus mission, making repeated passages through the geysers with instruments sensitive enough to detect complex biosignatures, could begin to address this question, but it has not yet flown, and until it does, the answer remains simply unknown. The exact interior structure of Saturn, how large its core truly is, how diffuse its boundaries are, how helium is distributed throughout the interior, what exactly happens in the transition zone where metallic hydrogen gives way to the ordinary liquid and gas above it, is known only in outline. Cassini's final orbits gathered gravitational data of unprecedented precision, and scientists are still working to reconcile that data with models of what Saturn's interior could look like and still produce the gravity field that was measured. The models that fit the data best tend to be more complicated than the simpler layered picture that older textbooks describe, with a fuzzy, extended core region similar to what Jupiter's data also suggests. But the details remain an active area of theoretical and computational work, and there are smaller mysteries scattered throughout the system. Why does Saturn's north polar hexagon have exactly 6 sides rather than 5 or 7? The answer lies in the specific ratio of jet stream speeds and rotation rate at that latitude. But the full theoretical picture of why that ratio produces the stability and longevity we actually observe is not completely worked out. Why does Iapetus have a ridge running along its equator, a mountain range circling the entire moon at its widest point, a structure unlike anything seen on any other solar system body? Several hypotheses have been proposed, involving material accumulated when Iapetus rotated faster early in its history, or material that fell onto it from a former ring system, but none has been definitively confirmed. What controls the exact timing and intensity of Saturn's great white spot storms, which have occurred with rough regularity but not perfect periodicity over the years they've been observed? These questions sit alongside the larger ones, patient and unresolved, waiting for the instruments and the missions and the theoretical frameworks that will eventually give them answers. Science is, among many other things, the slow and steady accumulation of better questions. The history of Saturn observation is a history in which each new instrument and each new mission revealed not just new answers, but new questions that couldn't have been asked before the previous round of discovery. Galileo couldn't ask what the rings were made of because he couldn't identify that they were rings. Huygens identified the rings but couldn't ask whether they were a solid sheet or separate particles. Maxwell answered that theoretically, which led to questions about resonances and gaps. Cassini the astronomer discovered the main gap. Cassini the spacecraft discovered that the gap isn't empty and measured the reign of ring material and the age of the rings. Each answer opened onto the next question, the way each hill crest reveals a further horizon. The chain of questions extends into the future, and the next link in it will be Dragonfly, and after that whatever comes to Enceladus, and after that whatever follows those. Each mission will find answers and find new questions, and the universe, as it always has, will prove to be somewhat more complicated, somewhat more interesting, somewhat more deeply structured than the previous round of investigation had suggested. Another open question concerns how common Saturn-like ring systems may be around planets elsewhere in the galaxy. We have discovered thousands of exoplanets, including many gas giants, but detecting rings around them is extremely difficult. A large ring system could, in principle, change the shape of a planet's transit as it passes in front of its star, adding subtle features to the dip in starlight. But the signal is faint, and many other effects can mimic it. If ring systems like Saturn's are common, we may not yet have the tools to recognize them clearly. If they are rare, then Saturn is even more precious as a nearby example of a planetary structure that may not occur often. This question connects Saturn to the wider study of planet formation. Rings are not only decorations around mature planets. Disks are central to how cosmic structures form at many scales. Young stars have disks. Young planets may have disks. Moons form from disks. Rings may be the remains of disks, the debris of collisions, or the temporary aftermath of tidal destruction. Saturn's rings therefore serve as a small, nearby laboratory for disk physics, a place where gravity, collisions, waves, gaps, and resonances can be studied in detail, then compared with much larger disks around newborn stars and planets. This is not a frustration. It is an invitation. There is something powerful in realizing that none of this was designed. Gravity and ice and orbital mechanics, left to their own behavior over millions of years, have created something that reliably takes human breath away at first viewing. There is no plan behind it, no intention, no design principle in the human sense. Just physics, doing what physics does, and the result happening to be one of the most immediately striking things any human telescope has ever been pointed at. That seems worth sitting with for a while. The most beautiful thing in the solar system, made entirely by accident, entirely by physics, entirely without awareness of its own beauty. Existing right now, during this particular moment in the solar system's history, at a size and brightness that will slowly diminish, a structure that is already, even as we look at it, falling gradually apart and falling gradually inward, its particles drifting towards Saturn one tiny increment at a time, century by century, to be absorbed eventually into the planet's atmosphere. None of which makes it less beautiful in this moment. Perhaps it makes it more so. As we come toward the end of tonight's journey, let's linger for a moment on what it would actually look and feel like to be near Saturn. Not on it, not inside it, but nearby, in the space around it, close enough to see the rings from a perspective no human has ever actually had. From a spacecraft positioned a few 100,000 kilometers above the ring plane, looking down at the ring's edge on, what you would see would be almost impossibly thin, a razor-sharp line cutting through the field of view. So thin you might almost mistake it for an optical artifact, a scratch on the lens of your spacecraft's camera rather than a structure hundreds of thousands of kilometers wide. This is the famous effect of the ring's extreme thinness. Seen edge-on, they nearly vanish. Rotate your perspective 90 degrees. Now you're looking at the ring's face-on, from above the ring plane, and suddenly the full scale becomes apparent. A vast, flat disk spreading in all directions, structured into bands and gaps, the B ring bright and almost luminous in the reflected sunlight, the Cassini division a darker band separating it from the A ring, the faint inner C ring barely perceptible against the darkness of Saturn's shadow behind it. The rings stretch so far in all directions that a human standing within them would have no sense of their outer boundaries at all. They would simply extend to the horizon and beyond, a flat plane of ice extending in every direction as far as the eye could see. Within the rings themselves, if you could somehow survive there, impossible for a human, but imaginable, the experience would be strange and quiet. The ring particles around you are moving, not stationary, all flowing in the same orbital direction around Saturn at high speeds. But because they're all moving at nearly the same velocity in nearly the same orbit, relative to one another, they would seem almost still. You might drift slowly past a chunk of ring ice the size of a house, tumbling slowly end over end, its surface sparkling faintly in the distant sunlight, moving past you at perhaps a few meters per second, the pace of a slow walk. The sky above and below would be open, black, sparsely populated by the other ring particles around you, each one drifting in its own orbit, the whole structure organized and orderly even at this intimate scale, the chaos of billions of separate pieces of ice somehow resolving, when you zoom out enough, into those clean, concentric, luminous bands. And above it all, filling a significant portion of the sky, Saturn itself, the enormous, banded sphere of cream and amber and pale tan, its hexagonal polar vortex visible near the top if you're positioned in the northern hemisphere's perspective, the gentle shadow of the rings falling across the planet's cloud tops in a broad curved band. The sun, from here, would look smaller and fainter than it does from Earth, but still by far the brightest object in the sky. A dazzling point of light 10 times farther away than it is from us, still more than bright enough to illuminate the rings and the planet with a soft, golden white glow that makes the ice sparkle and the cloud bands glow. This is a view no human being has ever actually seen. Voyager 1 and Voyager 2 passed through the Saturn system in the early 1980s, and Cassini orbited there for 13 years, but no human has gone. The images we have come from cameras carried by unmanned spacecraft, interpreted and processed by scientists working from 1.5 billion kilometers away, imagining what the view would be like from where their instruments were traveling. One day, perhaps centuries from now, people may actually travel to Saturn's neighborhood and see all of this directly. They would arrive, presumably, in the northern or southern approach to the system, and Saturn would gradually grow in their viewport from a bright point of light to a disk to a planet with visible features. And then, at some point in the approach, they would begin to see the rings, first as a thin line, then as a structure, then as the full, extraordinary reality of what's actually there, rendered in the actual light of the actual sun. The same effect that Galileo first noticed in 1610, that Huygens first correctly identified in 1659, that every amateur astronomer since has experienced through a backyard telescope, but seen properly for the first time, with human eyes, from inside the Saturn system itself. That would be a remarkable moment in human history, a moment worth waiting for and worth imagining now while you drift towards sleep. The universe is full of structures that seem too perfect, too ordered, too beautiful to have simply happened without intention. Saturn's rings are one of the most striking of these. Ice fragments in orbit, organized by physics into concentric, luminous bands that last hundreds of millions of years before gently dissolving back into the planet below. But that's what the universe does when you give it enough time and enough gravity and enough ice. It makes something beautiful, not because it's trying to, not because anyone asked it to, just because, under the right conditions, with the right materials, the physics works out that way. Debris finds orbits. Orbits flatten into disks. Disks organize into rings. Rings catch the light of a distant star and scatter it back into space in patterns that any creature with eyes and a capacity for wonder will find impossible to look away from. We are, all of us, beings who happen to exist during the narrow window of time when Saturn wears its current rings. Not when it wore an earlier set, not when the next set will appear, but this specific one, this particular configuration of ice fragments from this particular destroyed moon, organized by this particular arrangement of shepherd moons and resonances into this particular pattern of brightness and shadow and gap and band. In 1 billion years, this view will be gone. In 5 billion years, the sun will have changed so dramatically that the entire inner solar system will be transformed beyond recognition. Saturn will still exist, probably, but what surrounds it will be different. Right now, tonight, from Earth, on a clear night away from city lights, you could go outside and find Saturn in the sky, a steady, golden white point of light, and know that what looks like a single dot contains, within its immediate neighborhood, all of what we have talked about tonight. The hexagonal polar vortex, the titanic storms, the 285 confirmed moons, Titan, wrapped in its orange haze, its methane seas sitting dark and still in the northern polar night, Enceladus, venting its ocean into space from its tiger-striped cracks, and the rings surrounding it all, thin as a breath, bright as snow in sunlight, falling slowly apart, beautiful and temporary and indifferent to whether anyone is paying attention. The universe doesn't need us to be watching to continue its slow, extraordinary work. But there's something to be said for paying attention anyway, for finding, in the middle of an ordinary night, a small point of golden light in the sky, and knowing what it is, and what surrounds it, and how long it took to understand any of it, and how much is still not understood. For letting that knowledge sit quietly with you as you breathe and as you rest, not demanding anything from it, just holding it lightly, the way you hold any beautiful thing that you know you cannot keep. Saturn will be there tomorrow night, and the night after, slowly moving against the background of stars, completing its vast, patient orbit, its rings catching sunlight in their patient, slowly dissolving way. You don't have to hold any of it tightly. Let it drift the way the ring particles drift, gently, in the direction gravity is taking them, without resistance, without urgency, simply moving. That's enough for tonight. Rest well. The rings are still there, in the dark, whether or not you're watching. They don't need your attention to be beautiful. They simply are. And so, for now, let yourself be still. Good Good night.